Hey guys, today for math I'm going to teach you how to identify the characteristics of exponential growth and decay and graph exponential growth and decay. Let's start by identifying the characteristics of an exponential function. If the exponential function was a growth factor, if it has a growth factor module, you'd use the equation a parentheses 1 plus r to the t power. Right there. If it was a decay factor, then it would be 1 minus r to the t power. A question someone might ask is, how can you tell whether a function is a growth or decay? Well, one way you can tell is by simply looking at the difference in the parentheses as in earlier in these two. If the number in the parentheses is less than 1, then it is decay, and if it's greater than 1, it would be a growth. Examples are, if the equation was y equals 6 in parentheses 0.32 to the x power, or y equals 2 parentheses 1.05 to the x power, you would know that the first equation right here would be decay, because this number right there is less than 1, which makes it a decay. And this question right here would be a growth, because this number right here is greater than 1. So any number greater than 1 would make it a growth, and any number less than 1 would make it a decay. Something I forgot to mention earlier is what each letter stood for. So let me explain that now. A equals the amount of time given in the question. P equals the starting amount that was given to you. R equals the growth rate, and in most cases R would be a decimal, so remember that. It's normally seen as a decimal, so I'm just going to put a decimal right there. And then T, which is obviously a universal letter for time. And sometimes you'll need N, which is the number of times per year. And the number of times per year. The only time you'll need N is when we were using the compound interest formula, something I forgot to mention earlier. And the compound interest formula is A equals P parentheses 1 plus R over N to the NT. I'll show you guys in a second. Compound interest. Alright, as I just explained, A is amount, P is starting amount, R is growth rate in a decimal form, T is time, N is number of times per year, and you're only going to need M in compound interest formula, which is this right here. A equals P times 1 plus R over N to the NT power. Let's get into a little graphing. The first rule that you need to know is when you're dealing with a graph in an exponential function, you should know that the domain, or D, is always all real numbers. And then if you pay attention, you'll notice that the range and the asymptote will always be the same. So there's the two basic rules I can give you right now. Let's use this simple equation here to use as an example to graph. When I graph, the smart thing for me is for the x's, I would just simply get a number, excuse me, I would just simply get a line, whatever this is called, I don't know what it's called, I forgot. But anyways, yes, you could just put in the points like -1, -2, 0, 1, and 2. And you could just simply plug those in for the x to get the y. And when you do that, you get 1/4. When you plug in -1, 2 to -1, you get 1/2. You get 1, you get 2, and you get 4. Alright, so when you plug those into the graph, you get right here, right here, right here. And when you graph that, you'll see that'll be a significant growth, as in right here. And if you pay close attention, you'll notice that the line will never actually reach a certain number. And for this case, which is the line will never hit 0, and the line that'll never hit is called the asymptote. So you already know the asymptote right here equals 0. And like I told you earlier, the range of the asymptote will always be the same. So you can just put y right here is greater than 0 because it's always going up. The reason why it's greater than is because this is a growth function that's going up. If it was going down in this direction right here, it would be less than, and this would be exponential decay. But this equation is exponential growth. And the domain is all the numbers as taught earlier. So that's how you graph an exponential growth function. Okay, so let's do a question that requires using the compound interest formula. I have a question right here that is already solved, so I'm just going to reread it and go through it with you guys. Okay, it states, you deposit $4,500 in a savings account that earns 3.5 annual interest. Find the balance for 2 years if it is compounded annually, monthly, and quarterly. Okay, the first thing I did is that I took this and I found everything. Well, I knew that P is the starting amount, and the starting amount they gave us was right there, 4,500. So I put it right there, and you put 1. And R is the growth rate, and it said the growth rate was 3.5%. So if you move that to a decimal, you get 0.035, and that's what I did. And N is the number of times per year. And the first one I did was annually. So annually means 1 time a year. So you simply put 1 for N, and you put in both ends. The one right here in the parentheses, and the one that's in the exponent. And you put T in the time, which is years, and it's been 2 years. So when you plug all that in and you use it, you get that much for annually, which is 4,820.51. And then you do the same exact equation, but since it's monthly now, where the 1 should be, you should put 12. So right here, right here, this number would become a 12, and that number would also become a 12. And when you do that, the number would be this much, which is 4,825. And then quarterly is only 4 times a year. So you just simply change the 1 to a 4, and the 1 right here to a 4. And it's 4,824.82. And if you notice, all the numbers are similar, and it's because when you're using these, the number should be very close, and it should be within like 99 point something % to be close. So that's it.